Thanks. All right, so it's K2 ET, K2 concentration of ET.
That's your Michaelis?
I think so.
You not simplified that yet?
Well, on the back there's other things. But
okay. Your ultimate equation you want is V naught equals your Vmax times your substrate all over Km plus delta S. And that's how you... I guess that stuff's important. So the whole idea, right, is you have enzyme plus substrate yields for ES, which makes E plus P. This is your very basic, what an enzyme does. Substrate comes and binds, product's formed and it's released. Now,
real quick, there's a question that asked for the equation of an enzyme reaction. Would that be it? Okay.
Yeah.
Okay.
And this is very basic. The whole idea with kinetics is you got to remember, and you're going to learn a little bit more of this, but it could really be E plus S, makes it ES, and then that goes to EP, which then goes to E plus P. So other enzymes go different routes, but we're going to, Michaelis Menton just focuses on this generic form of an enzyme. And so this is your K1, this is your K minus 1, this is your K2. Right? Your Km tells you how tightly things are binding.
Okay.
It's kind of like the whole idea of a KD, but not really.
Okay.
KD tells you, if we don't take into account K2, KD tells you how tightly it binds based on, well, if K1's bigger than K minus 1, then obviously it's going to bind tighter.
Okay.
Km kind of tells you that, but it also takes into account K2.
Okay.
Because if I'm not mistaken, it's, what is it, K minus 1 plus K2 all over K1.
Yep.
And so you think K1 is the only thing that comes to Ks. We're assuming that really once it's turned into product, we're not going to come back to E plus S. So in K2 and K minus 1 are how fast they're leaving. Yes.
Where KG would be more for like ligands and things like that. Ligands.
Yeah, because ligands won't be changed into product.
Whereas this. So
there's no K2. So I think we can assume if K minus 1 is substantially, like the 100th power, bigger than K2, then our Km equals our Kd, meaning not many things are changing into product.
Okay.
So Km tells you, how tightly does this enzyme want to hold on to? And have you learned about Kcat yet? Okay. This is more the theoretical part. So Km really tells you, you can think of it, Km tells you this point. Vmax tells you how fast it's being turned into product. Like at what concentration do we reach Vmax? How, with this much substrate, what concentration of substrate do we need to maximize how quickly we're being changed to product?
Okay.
It's a very general. Do you have an equation for Vmax?
Yeah. Vmax is K2 times the concentration of E total.
So that concentration of E is going to be, and then times K2, that's how quickly we're changing into product. And you have to take into account how much enzyme you have, because you only have like 2 enzymes, you're not going to get that much product, even if it's changing into product quickly.
Can you say all that again? I'm sorry.
Yeah, so
Vmax. Maximum rate, right?
And I think really it's best to think of this more theoretically, just because, like you said, there can be a ton of different equations for an enzyme. This is generic. Vmax is your total concentration of enzyme, so how much enzyme you have, times how quickly, once you get substrate bound, we're changing the product.
Okay.
So really Vmax tells you really how quickly you're getting product. Because if you only had like two enzymes,
Okay.
they might change it really fast, but you're not going to see a lot of product.
Yeah.
So you might think, well, if you didn't know how much enzymes you had, you might be under the impression that the enzyme's not very good at making product.
Yeah.
When in reality it is, there's just not a lot of them. So that's why you got to take into account both factors. To determine
So
Vmax.
it's a theoretical rate because because K1 could be really large and could be it could be disassociating really fast, right?
Or yeah, your K minus one, it could be.
Yeah, that's what it K minus 1.
Yeah.
Really large.
And so
Okay.
even though these things are mathematical and they're applicable, I think really the understanding you need to first think, well, what is this telling me
Mhm.
more than what's the mathematical equation for it?
Okay.
Cool.
And so Vmax is the maximum rate and Km represents what again?
Cam, how tightly, brother, if you want good explanation, brother, let me explain to me. I was really confused. This was the only section where I actually read the book, and I really tried to understand it, just because
Mm-hmm.
I was sitting just barely at A minus. I was really worried that this section would kill me. So I got 100% on this section, because
Nice.
it's like my first one, because I studied so hard, because it's so hard. It's hard material. But I went and talked to Brother Rubish a lot. Sometimes I feel like you go talk to the teacher who's not teaching you, they don't hold back information or teach it. And so he taught it. It made a lot more sense when I heard from Brother Rubish, just because he wasn't testing me on it.
Mm-hmm.
Teachers speak a little bit more freely. And so I talked to him, but Km, he explained that's how tightly an enzyme will bind to something.
Mm-hmm.
And you'll eventually learn about Kcat. Kcat really tells you how good they are at turning it into product.
Okay.
And most enzymes in the body, there's Kcat, and I don't remember the equation for Kcat,
Uh-huh.
and you'll learn about it. But then what they do is they take Kcat and they divide it by Km. I can't think of the term, but there's a certain term for what value they get. And so most enzymes are around the same value.
Mm-hmm.
Their Kms and Kcats might be extremely different to each other, but the ratios of them are the same.
That's
and
cool.
He related it to like students. There's a lot of students, if you have a really small Km, that means you have really tight binding. You get to K1 really fast, and your K1 is much bigger than the sum of those two. So the enzyme holds on to that substrate for a long time,
Mm-hmm.
and it binds tightly. And ones that tend to have a low Km, so if I put here, low Km equals increase of binding.
Increase button.
Here, an increase of Kcat equals an increase of your efficiency
Mm-hmm.
of turning it into product. Excuse me. So ones that have a really low Km tend to have a lower Kcat as well, because they hold on it tight. They don't got to be really efficient at turning it into product.
Mm-hmm.
Or they don't have to be quick.
Yeah.
Or maybe I should say increase speed of making product.
Uh-huh. So lower the Km, the higher the binding, just like with KD.
Exactly. Yep.
Cool.
And so you read as students, like some students, they have a low Kcat, so they take a long time to do things,
Uh-huh.
but they're really focused and they hold on to their work. They take a long time, but they do a really good job. Other students, they have a higher Km, they're a little bit sloppier in their work, but when it comes down to it, they can just get their work done really fast and it's done well. So
Mm-hmm.
if you think of an enzyme, if its Km's really slow or really high, it doesn't bind onto it tight, it's got to be able to turn it into product really fast. Because if it doesn't, then your enzyme's worthless and you don't need it. Same with if you bind really long time and you can turn it into product really fast, then you're wasting energy because you're taking energy to hold on to it and then you're taking a lot of energy to go really fast. So that's why the ratios tend to be the same.
Huh. Cool.
But Brother Lemon didn't really, at least when he taught us, I didn't feel it was covered very well, the Kcat. So just having that explained to me, I was like, oh, it helped everything make more sense to me.
Cool.
So your Vmax and Kcat, guess theoretically, you think of them the same even though they're not. Kcat's how fast it turns into product. Vmax is more how quickly you're getting product
Okay.
versus how much substrate you have and concentration of enzyme.
Okay. Cool.
If that makes sense.
So could Vmax kind of be a representation of the ratio? Like, it's not exact, but like, because the Vmax is how fast you're getting product.
Maybe if I do this.
I don't know.
So Vmax is when you plateau, and and usually you think of it like this.
Yeah.
Your Kcat is how you can think of it this way. Is really how quickly you're getting product. So it does deal with the rate, and your Km and Kcat deal with how quickly you're getting to the plateau. Changing your Vmax might mean your Vmax is now lower because you have less, it's dependent upon concentration of enzyme. So you have less enzyme, your rate's going to plateau quicker.
Okay.
But it's going to plateau at the same concentration of substrate.
Okay.
If that makes sense.
I think so.
So this point of, I mean, my drawing is amateur at best, but the point of plateauing is going to happen at the same concentration of substrate, but you're going to have a lower rate because your Vmax is, you're hitting Vmax quicker.
Okay, so Vmax is dependent on the concentration of the enzyme and the substrate, whereas Vcat is not.
Kcat.
It's just the rate of catalysis, basically.
Yeah.
Of the enzyme.
And do you want to look up, maybe we should look up the equation for Kcat, that might help make it a little sense. But I think the idea is if you change Kcat or Km, because they're interrelated together, you're going to reach the same Vmax, but you're going to reach it later.
Huh. What's this? Equation. ET times Kcat.
So that's not what Kcat is.
Units of Kcat? No.
Might be the first one there, yeah.
This one?
Kcat. Sometimes they. So this talks about the ratio and it's.
Yeah, that's okay though. We'll talk about it eventually, right?
Yeah. So yeah, like if you change your Kcat Km, you're gonna hit your Vmax later, but changing your Vmax changes like what your Vmax is.
Okay.
Makes sense. But this right here, to me, if you think more theoretically, help me understand it. Your actual application comes more with your, you need to know this guy, then your application of it comes more with the Lineweaver-Burke plots. Has he talked about those at all?
No, I don't think so.